Okay, let's start. So, hello everyone. I'm Xuanyu from University of California, San Diego. So today I'm going to present our works on synthesizing strongest and weakest specifications. So you might be wondering what this title means, and I feel like it is a little bit related to the last talk. We are both synthesizing predicates. But of course, this talk is definitely not about a single specification that is both strongest and weakest. That would be a contradiction. And instead, we are trying to infer two kinds of specification. So what are they, and why do we need both? Let's look at an example first. So now that we ask ChatGPT to write program for us, so suppose you ask ChatGPT to write a hash function using modular arithmetic, and it will probably give you two options, which looks almost identical, a times x mod m, except one used the modular operator and the other used the remainder operator. And as you may know, the remainder operator may produce negative output. So you are not sure which one is better, so you ask ChatGPT to generate some formal specification to understand the program. So for example, the output of the mod hash function should always be within 0 to m, and the output of the rem hash function should always be within minus m to m. However, those specifications are actually not enough to describe the program completely, as they only talk about the potential outcomes. So for example, the assertion on the right, doesn't really tell you that the negative part can actually be produced, because the program on the left also satisfies the assertion on the right. So the specification might just not be strong enough. So in fact, we need another kind of specification to describe the reachable outcome. So for example, here, this yellow formula on the left basically says that for every output within 0 to m, and when some other condition holds, then there exists an input x that can produce that output. And the right one are similar. So now we can safely conclude that, okay, so mod hash function is a surjective function on 0 to m, and rem hash function is surjective on minus m to m. Okay, that's good. And actually, the relationship between these two kinds of specifications is just a duality between over and under approximation. So why do we need approximation? The reason is that the formula we show on the screen is not a useful specification. It just restates the program itself. So we have an assertion language with limited expressivity, and on which we want to build the specifications. Here, the blue formula, what we call safety properties, over-approximate the program, while the yellow formula, what we call reachability property, under-approximate it. And although both of them share the same formula, say 0 less than or equal to y less than m in their formula, their semantics actually differ from each other. So safety means that the condition holds for every input x, and the reachability, on the other hand, means that every number between 0 to m can actually be reached for some input x. So here I have also shown the complete condition that makes all output reachable, which I omitted in the last slides. So the condition basically says that if the modular m is a prime, and the coefficient a is neither 0 or m, and once this condition holds, we will know that this hash function will be surjective and thus doesn't waste the output range. Okay, so how do we automatically fund those specifications? So that's exactly what our framework does to synthesize both the safety property and the reachability property to better describe the program. So the Loud framework takes as input a program and assertion language, and it produces two things: safety properties and reachability properties. And the program also comes with a query that describes the relationship between input and output variables. And you can see that in the query, there is an existential quantifier to model the input. And moreover, those properties are required to be incomparable and most precise. So the incomparable and most precise means that for the safety property, their intersection cannot be further strengthened, and for the reachability property, their union cannot be further weakened. So there actually has been a lot of existing work targeting this problem of specification inference. So how is our framework different from previous work? For example, there are some dynamic technique called DICON and QuickSpec. Actually, they learn specifications from the execution chases generated by some test inputs. As a result, they only guarantee the soundness over execution chases and give no guarantee on precision. Spyro, which is the work we built on top of, propose a way to synthesize the specification with both soundness and precision guarantee. But it is still limited to over-approximation. And our contribution is to propose a unified logic framework called LOUD. And it is for synthesizing both strongest over-approximation and weakest under-approximation for program with existentially quantified input. All right, so how does LOUD actually synthesize property? So there are two main challenges. First, it will synthesize both over and under approximations. And second, it has to handle queries with alternating quantifier, and I will explain why that's important next. So our synthesis algorithm actually builds on top of the Spyro algorithm, which only handled over-approximation cases. And it follows a CGIS type approach. It also uses positive and negative example to approximate the synthesis objective. And at a high level, the algorithm has three main primitives, and each of them can be implemented as a call to the solver. First, it will try to synthesize a property from the current set of positive and negative example. And next, it will check the soundness of that property. If the property is unsound, the solver will return a new positive example. And if it passed the soundness check, we then need to check precision. And if it is not precise enough, the solver returns a new negative example together with a more precise property. So by iterating through these three primitives, what we call synthesize, check over-approximation, and check strongest, we will eventually obtain a sound and precise over-approximation of the program. And because of the duality, it seems straightforward to derive a counterpart algorithm for under-approximation simply by flipping everything. But the things are not as simple because we still need to handle existentially quantified input. And let's see what will happen with this existential quantifier. So when we ask for a positive example, we are actually asking, OK, if there exists an example together with an input that produces this example. And that's fine. You could imagine that to implement this as a single call to the solver. But when you're asking for a negative example, the situation is different. Because a negative example means that it can never be generated by any input. So here we get an alternating quantifier. And the way we address this is through another layer of quantifier instantiation. Each time we generate a negative example candidate, we reduce the universal quantifier by checking only over a finite number of instances. And we have this loop to generate it and validate the negative examples. OK, if you don't understand those technical details, don't worry. Let's see how the LOUD framework works in practice and how it can be applied to real problems. So in our implementation, we implement this 5 subroutine as queries to the sketch solver. So sketch provides soundness guarantee, but only for bounded input size and bounded language size. And of course, one could also choose other way or other solvers to implement this primitive, and that's why this is a general framework. And as long as they're available, one gets an algorithm for synthesize sound and precise properties. And for evaluation, we have some simple program for specification mining, and we also have some case study to show its applications. For example, our framework can be applied to reasoning about nondeterminism or concurrency. And the key idea here is to use the existential quantifier to model the random schedule. So here I take the classic dynamic philosopher problem as an example. This formula describes whether a deadlock can happen under some random scheduling order. And if we use an over-approximation, we get some condition that must prevent deadlock. And on the other hand, an under-approximation gives us condition that may cause deadlock for some unlucky schedule. And our framework can also be applied to synthesize symbolic strategy for two-player games. So suppose two players are playing a game on a grid, and this formula captures the game process from the player A's perspective. And if we have an over-approximation, it means that as long as player A follows any strategy satisfy this condition, the player A will win no matter how player B plays. And on the other hand, if we have an under-approximation, it means that the player A follows some strategy satisfying this condition. The player A may lose if player B plays optimally. And if you are familiar with reasoning in Hoare or incorrect logic, you may already realize that our framework can also be used to find strongest or weakest expressible post-condition in both of this logic. And the idea is to use the existential quantifier to define the post-image of the given precondition P and the statement S. And here, the over-approximation corresponds to the post-condition in Hoare logic, and the under-approximation corresponds to the one in incorrect logic. So to conclude, we introduced our framework for synthesize both over and under-approximation, and we explore several applications. And our framework has good usability. For example, one of our collaborators asked us, after this paper is published, he asked us whether we could use this framework to find conditions that trigger the worst case complexity of the quicksort algorithm. And yes, our framework can successfully synthesize the formula showing that, quicksort reach n squared time complexity when the input list is reverse sorted. And moreover, we don't expect our framework to solve every problem since the scalability is always a challenge. But the principle of the approximation is widely reusable. So for example, by relaxing the problem definitions, we can design more efficient solution for some specific domain. So for instance, we apply this principle to synthesize abstract transformer for LVM, which led to our paper that got conditionally accepted in Povo next year. And it has an easy-to-remember name called Nice to Meet You, and it's turned out to improve some precision for data flow analysis in LVM. And that's all of my talk. Thank you for coming, and happy to take any question.
Okay, let's thank the speaker. Yeah, we have time for questions. Yeah, while answering question, I think the last speaker could set up the microphone. Okay, any question from the audience? Okay, I have a quick clarification question. You mentioned that during your reachability, you're checking the reachability. What you do is that you find a counterexample by inverse existential quantifier to universal quantifier, but you still have another existential quantifier, quantification. So I don't know whether that affects. So how do you find an example based on that?
That's a good question. And well, the key is that if you only do safety property, you got two existential quantifier, and they can be merged together. So that's good. But when you do reachability, it's like what I showed is kinds of have a existential quantifier followed by a for all. So you need so the out layer is a kind of synthesized from positive and negative example. But when you generate a negative example, you need another layers of counterexample guided, we call counterexample guided quantifier extension agent. So you can think it of like, we have two layers of counterexample guided synthesis.
Okay, I see, thanks. So, more questions? Okay, let's thank the speaker again.